So this is lecture 36. We're talking about Stokes' theorem, and actually this is one of our major theorems of vector calculus, right? Fundamental theorem of calculus, Stokes' theorem, and the divergence theorem. These are the standard theorems we share in Calculus 3. There's actually more towards the end of my notes, but that's not the formal required part of this course. But if you read past the divergence theorem in my notes, you'll see some other deeper results which come from what's sometimes called the theory of potentials. But this is one of our last major results to talk about, and essentially the Stokes theorem we've already seen already. It's really Green's theorem in a particular context. In the two-dimensional context, Stokes theorem becomes Green's theorem in this sense, and specifically in the following sense, that if you look at Green's theorem, really you're looking at the line integral of a vector field PQ, or you could think about PQ0 like I say here, and if you take that line integral, then the z component of the curl is exactly that, and so we've got that the line integral around the boundary is equal to the surface integral of the curl, around the appropriate area. Now we didn't know that this was a surface integral before, right? But this is in fact the you can interpret this as the integral which corresponds to that surface integral as it happens. And in fact, I'll now share with you a little argument that basically allows us to piggyback this result to something that's kind of three-dimensional. Well, it's not kind of, it is three-dimensional. Something that's like this. So here's a picture. So if you can excuse me, I say suppose S is some simply connected planar region like this, and with unit normal n hat consistently oriented, and so this is a piece. May call this piecewise planar region. Right, each piece is a little piece of a plane, and I want to assume they're consistently oriented as I've pictured here, right? Then we can apply Green's theorem to each one of these faces separately. Well, the Stokes version of Green's theorem, which is written in sort of a less XYZ fashion as the n hat component of the curl, and so like u and v are the coordinates, the parametric coordinates, if you will, on the face that's in discussion there. And so I can apply Green's theorem in the curl form of Green's theorem, or on each one of these faces separately, and so I can get Stokes' theorem to be true for each face, essentially, of this polyhedra. And then if I just add together these, if I sum Stokes' theorem for each face together, then what happens is the integration, the sum of all the faces of the area, and the surface integrals just gives me the surface integral over the whole shape, the whole surface, right? Whereas the integral, when I add together the boundaries, well, all the interior crosscuts, they cancel, just like we talked about in our proof of one of the proofs I looked at of Green's theorem. The same kind of idea. The crosscuts, the inner crosscuts cancel, and so there we go. That gives us what I call the baby Stokes theorem, which says that if S is a polyhedra S with consistent oriented boundary partial S, and F is differentiable on some open set containing S, then the line integral around the boundary of the vector field is equal to the surface integral of the curl over that surface. And so I just talked you through the proof, but the proof is in words. I forgot to say, this is from pages 365 to 374 of my 2020 notes, right? And as I've mentioned, this is a printout from a few years ago because I'm too lazy to print it out again in color, and well, it's kind of expensive. I should actually just fix all the errors and print it out once and for all, but one of these years here I'll get to it. Let's see here. Something I tell myself. Stokes theorem. Okay, so continuing, this is just a rehash of the proof I just went through. Add up the boundaries, add up the faces. The sum of the faces just directly gives you the surface integral over the whole the whole thing, and then again, the sum of the boundary pieces, you need that to notice that the interior boundaries cancel, and you're just left with the exterior boundary, which is this statement here. Now, so I say this theorem naturally extends. Theorem naturally extends to a theorem for most regular surface. I say mostly regular, which means we do not allow for. Well, I say mostly regular because we do allow for surfaces that have edges and corners. Essentially, since we're integrating over a two-dimensional thing, if you've got some sort of like one-dimensional crease, it's not going to change the integral. I feel like a sufficiently malevolent math student could come up with an example where it mattered, but for typical applications, it doesn't matter. Let's say that. If the edge or the corner is where the divergence is, and that divergence significantly contributes to the integral, well, then it might matter. But, that's part of a deeper discussion. We're going to assume our vector fields are nice enough on the surface or near the surface. There's always this condition, always this condition somewhere hiding in the theorem. Suppose F is differentiable on an open set containing S. That's kind of like forbidding the existence of those like jump singularities or whatever you want to think of them as at those defects in the surface where it's not regular. Like for example, if your surface is a cone, right? Then at the conical singularity, at the point of the cone, if something funny happens with the vector field, right? If it's not differentiable there, if there's some kind of non-trivial singular behavior of the vector field there, then it might matter to not to ignore that, We already have seen this in the one-dimensional context in calculus too when you study improper integration, right? If the function you're integrating is, it depends on the nature of the singularity at the boundary point whether or not it actually makes the integral blow up or not, Both can happen. That's why it's an improper integral. The same thing in principle should be able to happen for higher dimensional integrals, but we don't really have examples that we cover in this course about that. I'm just talking about it, so I'll shut up. Stop talking about things I don't have examples for. So, and then of course this Stokes theorem doesn't just hold for polyhedra, it holds for a simply connected surface with a consistent oriented boundary, like so. And so the first proof I would give is just, well, take your surface, whatever it looks like, and then approximate it, Find your best polyhedral approximation with 1,000 faces, and then believe in the existence of, higher polyhedral approximations for the surface. Like you can always increase the number of faces in your, polygonal approximation to the surface. You could think about this as this is actually if these were all triangles, this would be what's called the triangulation of the surface. And topologists have spent considerable effort proving the existence of triangularizations of surfaces of a particular type. Anyway, given a surface which allows such a triangulation, then you can take the number of triangles increasing more and more and more, and you can always apply Stokes' theorem on each subtriangle, and so passing through the limit, passing the previous result through the limit of the number of triangles going to infinity, we get a proof over a simply connected smooth surface. But like I said, the reader should find this limit geometrically obvious but analytically daunting, right? Like to actually go through the details there requires a deeper analysis than we're going through in this course, but it should be intuitively clear that that's not unreasonable. Anyway, here's an actual example. Let vector field F be minus y. I'll zoom in a bit here. Zoom out a bit. I gotta get it. I've been wiping the camera lens with a Kleenex, but it seems like it's a little bit fuzzy in the corner there. Of course, it could be my eyes. I need to get glasses. Let's see here. All right. Minus y x z. We want to find the flux of this vector field over half of the outward oriented sphere with z greater than or equal to 0. So a picture of that, roughly speaking, is just let's see here, like, all right, so like it's upper, so the normal's like this, and so if you want to understand the boundary, it's the equatorial circle, this guy down here, right? And so the boundary of SR plus, as I've called it, I've made red, and just to be clear, if you can imagine yourself walking around on top of the surface, right? Like imagine yourself a little dude, walking along the edge here. Put top hat on, standard top hat. So Mr. Top Hat there walking along the edge. Then if he's on top, then if he's walking in the positive sense, then the surface should be on his left. So that's the rule. Like if you imagine yourself walking around the boundary, if you're walking in the positive sense, the surface should be on your left. And so that means that there is it goes this way. All right. Which incidentally, if I were to imagine gripping the z-axis and wrapping my fingers around that boundary, it would be the same. It's like this. So in other words, this is essentially the direction of that is described by theta hat. It wraps in the counterclockwise direction around the z-axis. All right. So, okay, well then, let's look at it. So what do I want to do? I am parametrizing the equatorial circle right there, and I'm going to apply Stokes' theorem to calculate the curl, the flux of the curl. Oh man, where was I? I'm going to apply Stokes' theorem to calculate the curl of that vector field, the flux of the curl, but I'm never actually even going to calculate the divergence, the curl, right? I mean, you could calculate the curl. Let me remind you, the vector field f here is equal to minus y x z. All right. Oh, by the way, this is in some sense an abusive notation. I should really always write like f of x, y, z equals to this, but it gets tiring after a while, so we just write f equal to that with the understanding that we're evaluating f at the point x, y, z, Anyway, by Stokes' theorem, this flux integral is equal to that line integral, and the mechanics of that line integral is I put x equals to, I just had it on the previous page, but the parameterization oh, curses. Sorry, I'm out of frame there. There we go. The parameterization of that equatorial circle is x equal to r cosine theta, y equals to r sine theta, and z equals to 0, right, for 0 less than or equal to theta less than or equal to 2 pi. And so that's why this line integral is integral from 0 to 2 pi. For y is r sine theta, so that's why I put a minus y, which is minus r sine theta. X is r cosine theta, that's why I put r cosine theta here. 0 is 0. And dx is minus r sine theta, dy, d theta is r cosine theta, dz is d theta is 0, so we get that. Take the dot product of that thing, you get r squared sine squared plus r squared cosine squared, which gives you r squared. And then you integrate that, and you get yourself a 2 pi r squared, and there you go. And so that, that's much easier than, say, calculating the curl of this and then calculating that surface integral, right? So this is a pretty nice result. My next example, I say, okay, same vector, right? Same vector field, but now I'm going to calculate the flux over the half of the outward oriented sphere, rho equals to r with z less than 0. All right, so I'll draw a picture of this one. So here's the SR minus, as I call it, right? And this time, imagine Mr. Top Hat he's walking down here, right? Because that's where up is for the this surface, right? The normals are like this, right? Outward oriented. So there's your normals like that, and sorry about that. So then if we imagine him walking in the upward direction, right? Well, on the upper side of the lower hemisphere, and the left, what's to his left is the equatorial circle, but how's it go? Well, it would be like he has to be walking this way, right? And then back there he's walking that way, right? So in other words, the boundary of SR minus, oh man, the boundary of SR minus is like that. And if you go back to the previous one, it's actually minus the boundary of SR plus, right? So it's the opposite. So so we can use the result of the previous problem and just get minus what we had in the previous time. See, because the cool thing here is, even though the previous problem was like calculate the flux of the curl over the upper hemisphere, right? The next problem is calculate the flux of the curl over the lower hemisphere. The upper and lower hemisphere share the same set of points as their edge, namely the equatorial circle. It's just that the positive induced orientation is opposite. So that's why we get a minus for this one, whereas we get a plus for that one. So that's pretty cool. I should also mention that there's like an easier way to understand why this has to be minus that in view of the divergence theorem. But I better leave that for later. So I'll probably forget to come back to this, but just comment. You can use the divergence theorem on the vector field curl of f to see that the vector field of the curl, the flux of the curl of f over the whole sphere has to be 0 by the divergence theorem. All right, anyway, moving on here. And once more, let's see what's this next example about. I will eventually get it in frame. I say once more, think about the vector field minus yxc. Since f is differentiable in R3, we can apply Stokes' theorem to any simply connected surface. And if that consistently oriented boundary is the surface of SR plus, then the flux of the curl is 2 pi r squared. So what I'm saying here is like, if you take a surface, right? And okay, so originally this is SR plus, right? Let me scooch over here so you can see my picture. Sorry about that. So this is my original SR plus, right? And so the boundary of it is, as we discussed, you know, like so. And like here backwards, right? Thing is, if I can take that and you just kind of imagine it being a flexible sheet, right? And imagine blowing into it, and you blow SR plus out into some kind of weird wiggly whatever surface like that, you know. But the edge of the surface is still down here. It shares the same edge. Because the vector field minus yxz, right, is differentiable on all of R3. It doesn't matter as long as this new blue surface shares the same, you know, as long as it's oriented outward like that, you know, and it takes the edge of it to be that same equatorial circle, then we're going to get the same 2 pi r squared for the integral of the curl over that blue surface. So that's very, very interesting, right? Because that means that we can deform the hemisphere to something else and still get the same answer. Like, another thing you could do is you could squash the hemisphere to a disk. The flux of this curl through the disk, the equatorial disk oriented upward, is also 2 pi r squared. So there's tremendous flexibility in Stokes' theorem once you understand this. All right. And so like the next example, 7.76 is basically going to give you a argument that is motivated by the previous pair, well, previous, not the immediate example before, but 7.74 and 7.73 are an example of this. That if you add them together, then you get the integral of the curl over the closed sphere is 0. And this is saying that if you have any closed surface, and you have that f is differentiable on some open set containing the surface, then the integral over that closed surface is 0. A closed surface is one for which the boundary is empty. All right, closed. So, you know, so incidentally, that means that the formula we wrote for Stokes' theorem naturally extends in the case that, if the case that this is empty, well, of course that's 0, right? So the integral over the curl of the flux of the curl over the surface is just 0 when the boundary is nothing, because if we integrate over nothing, you get nothing, which is 0. But anyway, the argument is you can take that closed surface, you can cut it into two halves, S1 and S2, and then when you look at the crosscuts, well, they're going to be oppositely oriented wherever those two surfaces meet together, just like, so this is just an example, right, but it's geometrically clear that if you take that closed surface wherever it meets, however you cut it, if this is like S1 and this is S2, and they're both, two halves of a consistently oriented, outward-oriented surface, it's closed. We, by default, take the outward orientation. All right, and you could do the same argument for the inward orientation. We just flip my arrows around. But in that case, as we've just discussed, essentially, down here the orientation is like that, whereas up here, it's just like that. The boundary of S1 up here, the boundary of S2 down there. I should have used a different color. It's not too late. Boundary of S2 down here. Oh, it's very Christmassy. There we go. So they're the same point set. Like I've separated them for the sake of illustration, but like glue them together for the real surface, and it's the same set of points in opposite direction, right? So like boundary of S1 is minus the boundary of S2. So when you apply Stokes' theorem to each half separately, you get the integral of the flux adds together. You give the integral of the flux the whole thing, and then the integral over the boundaries cancel, and that's that. Now, we can also do Stokes' theorem for a surface containing holes. If you've got a surface with a simply connected, well, not simply connected surface, but a simply, a surface that has holes in it, all right, then if you extend your notion of boundary, just like in Green's theorem, the holes in the inside have to have clockwise oriented boundary, whereas the outer edge has to have a counterclockwise oriented boundary, assuming, of course, that like the normal is up here, right, for the surface, or perhaps I should say ds for the surface is up here, right? So again, if you can imagine yourself a little dude walking along the hole, if he's walking along, then the hole should be on his left. The surface should be on his left as he's walking. And if you look at it, if he walks like this, then if you can imagine little dude walking on that edge, the surface is on his left as long as the hole is like that, And likewise, if you can, zoom in here, I guess I can. The orientation of the holes are chosen such that if you can imagine a little dude walking inside the surface on the upper side, then the surface should be on his left as he goes around the hole, which is to say that the interior holes are clockwise oriented with respect to that normal, whereas the outer boundary, the outer edge of the surface, is counterclockwise oriented. So this is exactly the same orientation scheme we used for Green's theorem with holes, and it naturally extends to Stokes' theorem. Let's see here, so I have an example. And then, let's see here. I'll let you read. I'm trying to see if there's anything else I want to talk about here. So just to summarize what goes on in the rest of this section, sorry about this. So this example here, I have a pyramid with a square base on the xy plane, and the surface, so the boundary is at the base of the pyramid. Find the flux to the pyramid if the, alright, so like the surface is like this pyramid, right? I can't draw it. I'm trying. So this is the xy plane, is equal to 0 down here, right? And so here's my vector field, right? And the thing is that vector field is differentiable everywhere, right? So let's see here. So if I think it's upward oriented, right? That would mean that the boundary of S is like this, right? Like that. So of course you don't actually want to calculate the flux of the curl through these four faces of the pyramid, right? But what you could do is notice that the four faces, that like the boundary, the square boundary at the bottom, it's the boundary of the pyramid, right? But it's also the boundary of just the square in the plane. And if we look at the square in the plane, what happens when you evaluate f on the plane? Notice that like f on the plane, f of x comma y comma 0 is just equal to what, 1, 3, 0. So of course the curl of f on the plane is 0. So if I deform the pyramid to the square in the plane, I can easily see that the integral of the curl on the plane is 0, and consequently the integral of f dot dr is 0 because it's the same boundary. That's what this argument shows. And then I say, well, this is not terribly surprising since direct computation shows that the curl of this vector field is 0 anyway. So, but again, that's this idea of deforming one surface into another to make the either the flux integral easier or trivial. Pretty much all my trick problems are based on that trick. And then there's also a deformation theorem for Stokes' theorem, which says that if you have, if you have a surface like this, so you've got a counterclockwise oriented inner boundary and a counterclockwise oriented outer boundary, and if the curl of f is 0 between here and here, then it follows that the line integral around C in and the line integral around C out of f is equal. And that's true because this minus that is equal to the integral of the curl, right? So if the curl is 0, then these are equal. And that's the deformation theorem for line integration on a surface as motivated by Stokes' theorem. And here's the somewhat more careful statement of it. All right. Now, of course, we can apply that to conservative vector fields because, remember, one of the things was in R3 we said that well, here it is, right down here. Add precondition n equal to 3 and u being simply connected. So the reason for that, right, was that so if this is the surface, right? And if we take any loop in the surface, right, loop, then you can, if in the curl of f is 0, right, well, let's say this, if this is any loop in the surface, right, then we have that, well, certainly if the curl is 0, then if we can smaller loop, right? I call it loop bar. We can see that the integral around the loop and the integral around the loop bar they're equal. if the curl is 0, right? And because there's nothing stopping us from shrinking the size of that inner loop to 0, it follows that the integral around any loop is 0, provided that the curl of f is 0. That's a straightforward application of Stokes' theorem. That's a sketch of that. Okay, and then I'm discussing here a little bit more about the connection between conservative vector fields and exact forms. I'll probably come back and talk more about this when we talk about the next part of the course, differential forms. So yeah, you can read it for now if you want. And then finally, here's the Stokes theorem for any connected surface, possibly including holes. If you've got k holes, then you just take the line integral around the edge minus the integral around the counterclockwise oriented holes, if you like, and that has to be all equal to the integral of the curl over the surface. And so that's it. That is Stokes' theorem. Now, of course, at the end of the section, I actually have a proof of Stokes' theorem for a graph. And if you dig through the details of this, what's basically going to be said is you look at the graph, you parameterize the edge using either x or y as appropriate. And so the boundary is parameterized by either x or y, depending on whether it's a, parallel to the x-axis or parallel to the y-axis, the curve over that image. And then when you sort through the details of evaluating the curl at those edges, you end up with, basically an application of the fundamental theorem of calculus, or the net change theorem, if you like, in reverse. And then once you've done that, then you can look at it and go, whoa, that's a line integral of p over the appropriate edge. And then you put it all together, and that's essentially Stokes' theorem. So Stokes' theorem, and the details are a little lengthy, but essentially it's not much of a lie to say Stokes' theorem is the fundamental theorem of calculus. Just filtered through the mechanics of the curl and line integration. And of course also the setup of the surface integral, but really the heart of it is, again, the fundamental theorem of calculus, which is not terribly surprising. But here's all the gory details that if we had 5 hours of class a week, I would maybe go through, but we don't, so there it is. Now, I hope that's enough for you to try to do some homework with Stokes' theorem. Next up is Gauss's theorem, aka the divergence theorem. And just to give you a foreshadowing comment, all it says is that the triple integral over the divergence of a vector field is equal to the surface integral of the vector field. And this is over some region, let's say B, and this is over the boundary of B. So that's the next thing is, this is the divergence theorem. So anyway, that's what we're going next. So, and this is even more useful than the Stokes theorem, really, because this allows us to trade a surface integral, which is a pain, for a volume integral, which can be easy. So in retrospect, in fact, there's a fair number of calculations that I've done in the notes already with direct application of the surface integral that will be easier with divergence theorem. So anyway, that's up next. Thanks.